Picture water being pumped from a basement tank up to a rooftop storage tank. The pump must do two jobs: lift the water and overcome friction in the pipes. The fixed vertical lift is the static head, here 20 meters, no matter how fast we pump. But push more flow, and pipe friction rises sharply with the square of the flow rate. Sizing a pump means finding the flow where it balances both without tearing itself apart inside. So let us look inside a centrifugal pump, the workhorse of the process industry. Liquid enters at the center, the suction eye, where the pressure is lowest. A spinning impeller flings it outward along curved vanes, adding energy. By the rim, the fluid is fast and high in pressure, and leaves to the discharge. That central low-pressure eye is the pump strength and also its weak spot. Put the behavior on one chart: flow rate Q across and head H up the side. The system curve is what the piping demands, the static head plus friction. It starts at the 20-meter static head we just saw, and curves upward as friction grows with the square of the flow. The pump curve, from the manufacturer, shows what the pump can actually deliver. Highest head at zero flow, and falling as the flow increases. The pump settles where it gives exactly what the system needs, the operating point. Here, 50 cubic meters per hour at 40 meters of head. That is the real flow you get, and from it we size the motor about 8 kilowatts. Now the danger hiding in that low-pressure eye: cavitation. If the inlet pressure falls below the liquid's vapor pressure, the water boils while still cold. Tiny vapor bubbles burst out of the liquid right at the impeller inlet. They are swept along the vane into the high-pressure zone, where they implode violently, hammering the metal with tiny shockwaves. Repeated millions of times, this pits and erodes the impeller. You hear it as a rattling, gravel-like nose with lost flow and heavy vibration. To stay safe, engineers track net positive suction head. NPSH available is the real pressure margin the installation gives at the inlet, atmospheric head, minus the vapor pressure, minus the suction lift and friction. For our cold water system, that is about 5.8 meters. NPSH required is what the pump itself needs, here 4 meters. Available must beat required, with margin to spare, and ours does, so no cavitation. But warm the liquid, and its vapor pressure climbs, shrinking the available head. Drop below the required line, and the pump cavitates, and the damage begins. In practice, we prevent it by flooding the suction, cooling the liquid, or slowing the pump. This same method sizes pumps for cooling water, boiler feed, reflux, and transfer lines. Match the pump to the system, find the operating point, and protect that suction eye. 2 curves, 1 operating point, and a healthy suction head, that is pump sizing.